easy chair at home. Anyway, what'll happen is you just simply email James. He has a couple different emails, but you can reach him at properties@freedlist.org. He's our properties manager as well. And once he gets 3, 4 people interested in the class, usually he'll pull the trigger on it and they'll have a class. The hands-on portion he usually does on the weekend, Saturday typically. And James, do you still do it in the grass over here by Greco, or you go someplace else now? It depends. Okay. Well, we find someplace and you set up your telescopes, and actually as a group, you learn how to use it and navigate the sky and stuff. So that's available to you as well. If you want to then join some of the fun and kind of give back to the community, you have a couple different ways to do that here at EVAC. Number one, you can join the team that sort of staffs the observatory, about a 5-minute walk to the east over here. And you can see the email there that you would use to join that list. And you can volunteer your time like once a month or once every other month. It's not a set schedule. Essentially, Claude, the observatory manager, pretty much just sends out an email the last week of the month that says, hey, who wants to work next month at the observatory? And if you're available and you want to, you say yes, and he'll assign you a night. And if you don't want to, or you're traveling that month, you don't have to sign up. So it's just a good way to give back to the community. Also notice that on the second Friday of every month, you can bring your own telescope out here, and you can set up in the grass over here by the observatory, and actually the public can look through your telescope as well. So fun way to give back to the community. A second way is you can always also join and help host the private star parties that we do around the Southeast Valley here. So we go to schools, community centers, HOAs, wherever. We have an event, a couple events, I think, coming up next week. I love the one coming up next week. It's like 6 minutes from my house, so it's nice. Easy drive. Most of these events are about 2 hours long, so by the time you add the commute and the setup and the tear down, you're looking at maybe 3.5 hours. And it's quickly volunteer. Once you're on the list, you'll see what events are available. And if you happen to be free and you want to do it, you join. If you're not free or don't want to do it, you don't join that particular event that night. So anyway, just another way to kind of give back to do this. Why would you ever want to do any of this? Well, number one, it just feels good. On Christmas or someone's birthday, when you give them a gift they really like and they get all excited, you feel good about that. That's kind of how these star parties go. People want to be there. They want to see the sky. They want to learn things. And so when you show them something fun, they just get all excited about it, and it makes us feel good. So it's kind of a selfish motive, but it does make us feel good. You're also going to learn more about the sky and your telescope and so forth, because people are going to ask you questions, and some you'll be able to answer. And I can guarantee you some you won't, but it gives you an opportunity to go get on your phone and look up an answer really quick. And you end up learning a lot more doing these events. It also helps you build friendships. I mean, there's several people in here that unless I was involved in some of these things, I probably wouldn't know. So I see several faces out here, like Derek, for instance, and others, David Perry, several others, Jake, that I've met through these events. And it's just a good way to build friendships. All right, special announcements. We have a few of these. The first one is important, so watch this one because it affects us all starting next month. We had a board meeting this week, and we decided to do the following. We're gonna start a little bit earlier going forward from now on. So we're gonna start at 7 rather than 7:30, and you can see we have several reasons why we're gonna be doing that. We looked around, and most of the astronomy clubs in the area are starting at 7. You notice one in Tucson's actually starting at 6:30. I actually went on to the web, the internet this last week, and kind of looked around at other things that would run meetings at night. And I thought, churches. So I looked at a lot of churches and their websites. Pretty much everybody starts at 7. So we're going to start at 7 and try to end by 9, if at all possible. And the reason by 9 is because like last week, we had 86 people in this room. It was a huge room. And at 9 o'clock, we still had 86 people. But the speaker ended about 9:25. And by that time, more than 20% of the room had left. So we're going to go to a 7 to 9 schedule. And if you happen to get off work one Friday late or whatever, we still have Zoom. You can still join from home via Zoom as sort of a fallback position. So anyway, so that starts next month, and that'll go out on the Facebook page as well. That'll also go out on the EVAC announce email list as well. So that's one big special announcement. Some of you have seen this. This was announced a couple of weeks ago on Facebook and on the email distribution list. So we do have a spring star party Messier Marathon coming up. So save the date, please join us. It is going to be Saturday, March 9th is what it's going to be. This is a joint event between us, EVAC, and the Saguaro Astronomy Club as well. So we're teaming up together this year. It'll run from obviously dusk till dawn. It's an all-night event, particularly if it's Messier Marathon. And we will not have food there, but we will provide like midnight coffee and a snack. So that'll be available to us. Porta potties will be available out there along with a little hand wash station. I ordered those a couple of weeks ago. They'll show up on Thursday before, so March 7th, and they'll be there through the following Thursday. So you have some sort of facilities you can use. And there will also be some sort of recognition for those who choose to participate in the Messier Marathon part of the event. I just don't know what that recognition is going to be yet because my counterpart at the Saguaro Astronomy Club is the one setting that stuff up. So I'll be talking to him more. Anyway, it is at our Hovatter observing site. Some of you have been there, some of you maybe have not. But the directions were in the email announcement, they were on the Facebook announcement, and the directions are also on our website as well. And the directions are very good, very detailed. My first time actually out there was last November, and I found it straight away. No getting lost. It was pretty easy to do. So another special announcement. Then I think the next one is Bob. So Bob, you want to wander up here? You're all set. Bob Buchheim is going to be up here representing the Society for the Astronomical Sciences. And he is going to give us an opportunity to present or participate in something. Just hit the forward keys.
The first thing I'm going to do is make sure I've got the microphone right. Woody called me last night and told me that my voice is too soft and I need to channel my inner Chuck Berry, start campaigning like a Southern diplomat. So I'm here to invite you, which forward? Bingo. I'm here to invite you to register for the Society for Astronomical Sciences 2024 Symposium in June, online in the comfort of your home or in person in Ontario, California. Now, why would you want to do that? I'm hoping that some of you in the dark of night have said to yourself, I have seen wonderful things in my telescope. I wonder if my observations or the images I'm making might have some scientific value. Turns out that question was the subject of a 2-day workshop at the American Astronomical Society meeting in Albuquerque last June on the role of small telescopes in this new era of large telescope surveys. And the answer might surprise you. We had representatives from several of the large observatories, including TESS and LSST. We had professors from several universities. We had equipment manufacturers all there to discuss this problem for 2 days. And the answer was, in this new era of big surveys, the demand for small telescope observations is getting larger. LSST is going to put out an estimated 10,000 alerts per night. There are plenty of things that need our attention. Where does the amateur astronomer fit into this? There were 4 big areas. The first was collaborating with the professional researchers. Those big telescopes can see really faint objects, but each of them has a bright limit where the sensors saturate. Assassin, I think we heard a couple of months ago, saturates at about 10th magnitude. Can't measure anything brighter than that. The LSST is projected to saturate at about 15th magnitude. Can't measure anything brighter than that, which means their bright limit is roughly at our faint limit. So there's a partnership there, and the division of the night sky into faint objects for them and bright objects for us is still in force. Most of the big surveys have revisit times to monitor an object It changes over time. Revisit times, typically a few days, which is pretty amazing that you can see almost the entire sky every few days. But there are a whole lot of phenomena out there for which that is not rapid enough. For cataclysmic variables, you may need an observation every hour, every night for several nights in order to measure the fluctuations there. You've got the telescope and the time that can do that. Asteroid rotational light curves, you need a measurement every few minutes, all night, every night for several nights in order to determine the rotational state of that asteroid. So again, there's a partnership that demands amateur participation. Is Wayne Thomas here? Asteroid and planetary occultations. You need to be able to take your telescope to where the event is happening. The amateurs own that part of science. Second, many of the surveys noted that we need to augment the measurements that they're making. For example, the TESS satellite discovering exoplanets every night, its pixel is about 20 arc seconds in subtense, which means there's always more than one star on that pixel. And they rely on our kind of astroimaging measurements from that capability to unravel contaminating sources. How do you tell an exoplanet from a grazing incidence eclipsing binary star, for example? They need our help in able to do that. The TESS follow-up program is a real success of pro-am collaborations. Replicating results that have already been published in the professional literature. You know, the social sciences are going through a real crisis of replication. There are a whole lot of things that social scientists know and have published that just aren't right. If you try to do that experiment again, you get a different answer. There are a variety of routine but important observations that we can make with our instruments. Eclipse timings of eclipsing binary stars, for example. Great project, amazing to see. Astrometry of visual double stars. There's 10,000 of those that need to be touched, you know, once every 5 years. And that can keep a lot of people busy doing useful, valuable observations. Asteroid light curves. An astounding number of the published asteroid rotational periods are wrong, and they need to be replicated in order to unravel the problems. Similarly, if you're studying a particular type of pulsating star, I was told at 3 different conferences last year about the problem. If you're studying RR Lyra stars, you can get a catalog. Here are all of the RR Lyras in the sky. 20% of them are not RR Lyras. They're misclassified. We can help out with that problem. It's a really interesting project and a lot of fun. And we can continue to play an important role in what we called exploration. High risk, low probability of success observations that will never get funded at a big observatory. But we have the time and we can squander our observing resources wherever we want. And you know, a gang of us here have been doing stellar flare observations in a way that no professional observatory can. And there's been 2 or 3 papers published as a result of the work that these guys did. So the SAS Symposium is 2 days of technical presentations on this kind of results. And every year I come home with a couple of highlights. 2022, the stellar flares thing was a really big deal. The other thing we learned was eclipsing binary stars. If you've ever taken the Astro 101 class, you know they are critical to understanding sizes and masses of stars. It turns out photometry with a small telescope of an eclipsing binaries light curve combined with Gaia parallax readily available now, you don't need to do the spectroscopic challenge of radial velocity curves. Last year, the new generation of CMOS cameras has opened up speckle interferometry to small telescopes, meaning you can resolve binary stars that are separated by a tenth of an arc second, despite the fact that you live in an area where the seeing is 3 or 4 arc seconds. And you can start plotting orbital motion of an orbit that goes around in a decade or two. Amazing new capabilities. And one of our professional astronomers gave us a talk that reminded us there are things we still don't understand going on up there. Cepheid variables, probably the most important class of stars you learn about. Well, they don't always act the way the theory says that they will. Odd observations keep coming, and we can help with all that. We also have 2 workshops scheduled for extended education and discussion. This year, the morning workshop will be on the Global Meteor Network. Dr. Vida, one of the organizers there, will explain to us how we can participate in video meteor observations to measure meteor rates, the radiance of showers and how that radiant moves over the course of the shower, individual meteor trajectories. Through the atmosphere, you can project backwards to get the orbit the meteor had before it encountered Earth, and project forward to where the debris landed, if any. And maybe we have a lot of empty terrain here, find it. The second workshop will be on tricolor imaging for science. John Hoot, Gary Hawkins, and Brian Kloppenberg will tell us about that new single shot color camera technology and how you can apply it to scientific imaging. So come join us. This is the premier event for amateur professional astronomical collaborations. We'll discuss projects like I've mentioned and others. If this sparks your curiosity, join us. If you have questions, see me afterwards. I guarantee you go to this symposium, you're going to come back full of ideas that you want to try and amazed at what people like you are doing in their backyards at night. So see me if you have any questions, and I hope that you can come and join us. Oh, and the first 3 people that ask get a free copy of proceedings from a couple of years ago.
Thank you, Bob. Jake, you're going to be up right now, so hand up out here. So let's see here. Let me get forward here. So we have a member presentation here tonight from Jake. He's going to talk a little bit about some astrophotography things. So Jake, if you want to come on up. Just hit the down or forward arrow right in there and you're all set.
Wait, is it left, right, or up, down?
Down or to the right.
Okay.
So those 2, yeah.
Gotcha. Hello, my name is Jake LeAlcala. Some of you have already met me. Some of you have yet to meet me. I'm the events coordinator for the East Valley Astronomy Club. So I handle all of the school events and things like that. I am here tonight to give you a little introduction to astrophotography. Now, I wanted to ask, how many of you in the crowd already do astrophotography? Okay, good amount, so probably almost a third. So hopefully those of you who already do astrophotography will learn something new, and those of you who don't may have the curiosity afterwards to start doing astrophotography. So we're going to jump right into it. Oh, it's a little slow. Oh, wait a minute. Ah, okay, so you said right and down. It's actually left and down. Let's see. Okay, here. So what are the basics? What are the things that you are going to need to start doing astrophotography? Well, you are going to need a telescope, obviously, something that focuses photons into a small beam, increasing the magnification of said object. You're going to need a camera to capture those photons. We'll get into the cameras here in a moment. Depending on the type of camera that you use, you will need a computer of some sort. You can use a laptop outside next to your rig, or you can get a mini PC, and a mini PC will actually use Wi-Fi to transmit that data to your inside computer, which is nice if you live in a cold area. You're going to need a mount, and not just any kind of mount. You need an astronomy mount, which generally comes in the form of an equatorial mount, or go to alt-azimuth mount that's set up on a wedge. The reason you want the wedge or some kind of equatorial axis for your telescope is because of how the sky moves. And if you have just a standard up, down, left, right, you're going to get what's called field rotation, because essentially your camera is going to be moving this way. And if it's moving this way, the sky is going to appear like it's twisting, and that could cause star trailing, which is no good. You are going to want some filters, whether that just be a solar filter or some more specific filters, maybe to capture certain wavelengths of light that certain targets emit. And last but not least, if you are doing deep sky astrophotography, you are going to want a bat knob mask, and we'll get into that here in a second. Okay, so let's talk about some telescopes for astroimaging. These are referred to as astrographs. And essentially, an astrograph is a telescope that is specifically made for imaging to be hooked up to a camera. They're generally going to have faster focal ratios, smaller to medium-sized apertures. Some of the Cassegrains are going to have larger apertures, but we'll get into that here. So first off, we're going to have refractors. Everybody knows what a refractor is. I believe most, if not all of us, have used a refractor at some point. A refractor setup for imaging, however, is a little bit different. They're generally quite small and short. They have a short focal range or focal length, a small aperture, but a wide field of view. They're best suited to taking pictures of large swaths of the sky. Next, we're going to have Cassegrains. Now, there are a couple different kinds of Cassegrains. Generally, the most common is going to be a Schmidt Cassegrain. These are going to have a very long focal length. Even a small 6-inch Cassegrain is going to have a focal length of about 1,250 millimeters, and they go way up from there. They're going to have a larger aperture and a quite narrow field of view. These are going to be best suited to doing very small galaxies and, of course, planets, or chunks of the moon. Small portions of the moon's surface are good for that. Then we're going to have Newtonians. Now, these are kind of in the middle. You know, you can get them in a large aperture or a small aperture. They don't have a massively long focal length. So you're going to get a bit more field of view, not quite as much as a refractor, but more than the Cassegrain. These do have one plus or drawback, depending on how you view it, but the spider veins that hold the secondary mirror up are going to create that kind of the Hubble effect, where the star, I can't remember, what are they called? Diffraction spikes, thank you. So those can increase or decrease the aesthetics of an image depending on what your opinion of diffraction spikes are. Now, last but not least, among many others that I'm not going to mention, are going to be smart telescopes like the Sea Star that James has mentioned earlier. These are small little telescopes. They sit on a mount, and they are going to have their own built-in motors for operating the movement of the camera. Some of them have built-in filters. Some of them come with extra filters, maybe to photograph the sun. And these are controlled either with a computer or a cell phone. And that's nice because you can set the smart telescope up to take a picture and just kind of leave it there to do long exposures throughout the night. And then you wake up and you check your phone. Oh, hey, I've got a very nice process picture. Now, some telescopes are going to come with a mount, but some are going to require a mount. And generally, when you buy an astrograph, you're going to get what's called an OTA, or optical tube assembly. These are going to need a mount. Otherwise, your telescope's going to be sitting on the floor, and that's no good. Let's talk a little bit about focal ratio and FOV. So the focal ratio essentially is going to be the aperture or the size of the objective or mirror divided by the focal length of the telescope. And this is also known as an F number. So some refractors, for example, are going to be F4 or F3.5, F5, somewhere in that range. The Cassegrains are generally going to be F10 or F12, some even up to F15. Like if you were to get a, Maxitov, thank you very much for that. This is going to influence the field of view of the, or image circle, I guess you're going to get, that can fill up the sensor on your camera. Now, FOV or field of view is the size of the patch of sky that you or your camera sensor can see. There is a website that's actually quite handy called astronomy.tools, and essentially you can plug in all your information for your gear, your telescope, your camera, the sensor size, pixel size, all of that stuff gets calculated, and they will put up an image of an object that you can select from a long list and essentially see a little box drawn over the object, and that would be the amount of that object that you can see. Very handy for kind of calculating if you're shopping for something and you want to image a certain type of target, you can check the field of view on that. Now, as far as astronomy cameras go, these are going to be very small cameras. There's no controls on them whatsoever. They plug directly into a USB in your computer, and you're going to control them with some kind of imaging software. Deep space cameras are going to have some kind of cooling fan or heat sink system in the back, and that's going to essentially lower the temperature of the sensor. That's nice for getting rid of noise. Obviously, when you take pictures of space, there's going to be a lot of noise in certain circumstances. The cooled cameras are going to do a good job at combating that noise. Planetary cameras are uncooled. They're a little bit smaller, and the sensor size is a lot smaller because obviously the planets are quite tiny in our sky, and you don't need that big of a sensor. It's kind of wasted space. So those are going to be more optimized for high FPS or frames per second. You want to take as many frames in a short amount of time as possible because one, the planets are going to rotate, and two, the atmospheric turbulence is going to kind of mess about a longer exposure. So that is something to consider. You can use a DSLR or standard camera with a T-ring. Those, however, are going to require a couple different modifications to work for astro imaging, but they are a good option. And you will need an intervalometer, which is just a little controller that you plug into the camera to do the captures automatically. Let's talk about the Bortle scale, seeing, and some of those filters we mentioned earlier. So the Bortle scale is essentially going to be a map that shows a distribution of light pollution from city centers or large light sources. This is going to kind of wash out the more dim objects. Now with imaging, that can be combated with some filters, but generally you want to be in the darkest sky you possibly can. So there's another website I will mention here called lightpollutionmap.info where you can see the specific Bortle number of your area or your imaging place that you like to go to. Now seeing, we're all familiar with seeing. Obviously when we have bad seeing, stars are really twinkly, everything's kind of fuzzy in your eyepiece or through your camera sensor. There is a website here as well that I like to visit called cleardarksky.com. And essentially that's going to show you a little graph by the hour with some other information like darkness, seeing, cloud cover, those kinds of things. And that's a good thing to view ahead of time before you plan your imaging session. And quickly we'll go through some of the filters. You can use ultraviolet and infrared filters to kind of get rid of those ends of the light spectrum so that you're not wasting photons on your camera sensor. Those are generally going to be best for planetary imaging because it'll also help you focus a little bit. You're getting rid of those unwanted frequencies and saving space for the ones that you can actually see. For deep sky imaging, It's not as important, but if you are using a mono camera, which is essentially just black and white, those UV IR cut filters are going to kind of help with the focusing as well. Solar imaging, there's two different kinds of filters you'll get for that. There's hydrogen alpha filters, which are going to show you a lot more detail. And then there's white light filters, which will just kind of show you a ball that you'll get to see some sunspots. White light is generally best for visual, and hydrogen alpha is best for imaging. There are some capture and mount control softwares. Some that I have worked with are going to be SharpCap and Fire Capture, and these are essentially just going to control the imaging of the camera. You can control your exposure. You can change your histogram around, which we'll get to in a second. The mount control software, so those are usually going to be pretty general, except for one. Celestron has their own specific kind of mount control software called CPWI. Those you can download for free, and you plug your mount straight in, download some drivers, and you can get to aligning your telescope, and you're good to go there. So let's capture some photons. What are we going to need to do on our first night out? We're obviously going to check the weather beforehand. We're going to check a planetarium app or star chart to figure out what image we're going to take, what object we're going to image. We're going to acclimate our telescope for 2 to 3 hours before imaging, and this essentially is going to help cut down on that turbulence that we talked about earlier. You want to align your mount at least an hour prior to your imaging to make sure there aren't any bugs in your traffic or your tracking, and to make sure everything's going smoothly. You're going to want to test exposure, time, gain, and the histogram to make sure that your camera is taking images properly. Sit at your computer, for 10-15 minutes while you start your capture, just to make sure everything's going correctly. Make sure your parameters and things aren't going haywire. And then when your capture is finished, we're going to move to the processing side. Image processing is an art on its own. There's quite a bit more to it than what I've included here, but I wanted to try to cram some things into a small amount of time for you. So first off, we're going to have histogram and color correction. Essentially, the histogram is a graph that shows you the balance of the light spectrum. There's a black point, a white point, and a midpoint. And by controlling those 3 points, you can really bring the most detail out of your image. Color correction essentially is just getting the levels of red, green, and blue in your image leveled properly so that it looks correct. Now, I have a couple images of Jupiter that I've taken here. One of them is a little purple looking there on the bottom that has not been color corrected, and the one on top looks a little bit more like the normal Jupiter that we're used to that has been color corrected. Lastly, you're going to denoise, which is going to smooth out some of those rough pixels on your image. We're going to sharpen our image to make sure that it looks nice and clear, and then we're going to crop it to make sure that the object that we took is centered. Animation's pretty straightforward. You can take multiple pictures and cram them into a video to create an animation. And that would be it. Just to make sure to choose your kit with your preferred targets in mind. Weather is a limiting factor, so plan ahead. You want to take time to learn. It's not going to happen overnight. And trust the histogram. It will show you when your image is properly exposed. Thank you.
Perfect. All right, what we're going to do here is we're going to take a 5-minute bio break and kind of let people stretch so you're all relaxed and ready for Roger and his presentation. So 5-minute break. It's 8:15 on the clock back there. At 8:20, we'll start back up. So.
While they're working on the technical things, I'd like to introduce our speaker tonight. And before I do that, I'd like to ask if anybody has their cell phones in some position other than mute or silent, if you could take a moment to check those phones. Tonight, our speaker is Roger Windhorst, an astronomer and professor of physics and astronomy at Arizona State University. He received his PhD in astronomy in 1984 from Leiden University in the Netherlands. and did postdoctorate work at Mount Wilson and Las Campanas observatories. I assume that's in Chile, Roger?
Well, it was in Pasadena, but yeah, they have their
Oh.
observatory in Chile.
And remote.
No, that was real time at 7:47.
Okay. Roger currently serves as associate chair at Arizona State and is among 6 Arizona State faculty who were awarded the Regents Professorship appointment in 2006. He presides over the School of Earth and Space Sciences at ASU. In 2008, he became foundation professor of astrophysics at Arizona State and co-director of the ASU Cosmology Initiative. Roger's authored over 100 scientific papers and given over 125 lectures at seminars. Does this count here?
Yeah, it's,
126?
don't worry about it. I can't keep track.
Okay, all right. His research has led to a new understanding of how the universe began. He also studies black holes. His research focuses on astrophysics and space science. And he's the principal investigator of the Hubble Space Telescope and the Mid-Ultraviolet Bright Galaxy Survey. Roger is one of 6 interdisciplinary scientists worldwide for the James Webb Telescope. A member of the JWST Flight Science Working Group, and Roger is involved in the JWST science performance and critical oversight of its entire design and construction phase. Let's have a hand for Roger.
Thank you very much, Steve, Woody, Tom, everybody. It's an honor to be back. I've given this talk many times. I don't remember how many times, including here in this room. Although I never actually finished the talk because there was no data from the Webb telescope. That's different now. So instead of being just pure promises, it will be purely data. And I understand you already, how many of you heard a talk recently on the James Webb Space Telescope? A number of you, but not the majority. So I have, let me backtrack a step. I know it's a bad habit, but the Webb telescope, worse than your talk last week, was over time by 14 years, not by 20 minutes. So I'll try tonight to stay on time, provided that I have a watch in the dark here, which I can't see. But if I don't, then we can skip. Actually, what I was going to do is skip a few charts. The talk comes in 3 parts, right? Let's see. Thank you. In orange, everything orange is on the Webb telescope. So the first part is an update on the telescope itself. And some of you have heard that, but most of you haven't. So for the sake of time, I will go through that a little quickly, and forgive me if I just skip some charts. That's what the break time is for and the question and answer time. Then the second part is on the Webb first images, or the first year and a half now, and the cosmic circle of life. And then the third part will be on viewing the universe through the eyes of Einstein. And that'll be as far as I get. I also have charts on what Hubble has done and galaxy assembly and supermassive black hole growth, and how Webb can measure Earth-like exoplanets. I won't get to that unless you ask questions, in which case I'll run over time, so don't blame me. There is a link there, which Tom or Woody will forward you. That is a fresh copy of the talk. Does that work? There's a way to crash that, but I don't know how to do it. Yeah, as long as I don't click on the... I hope the folks on the internet can see my my cursor, which I will occasionally use. So first of all, I'll come with a warning. Asking NASA for Hubble images is like drinking from a fire hydrant. Yeah. Okay, this is the mild version. Asking NASA for Webb images is like taking a sip from the Niagara Falls. So children, please don't do this at home. We're going to be overwhelmed with real data tonight. When I gave this talk, I think in 2012 and 2014 and 2019 or 16, I don't remember here. I had no data, we just had fake data and Hubble stuff. Now we got the real thing. So that's what we're going to talk about today. I will so skip most of the first third of the talk, but I will say this. Hubble, the telescope, was named after Hubble the astronomer, who of course, here in green, and I'll try to use as consistently as possible the cursor rather than my relativistic jet over here, the laser writer, and the laser pointer. And it was named after Hubble, the astronomer who discovered the expansion of the universe. The Webb telescope, and by the way, Hubble was first conceived in the 1960s. I don't know where you guys were. I just got out of preschool. It was funded by Congress in '73, constructed in the 1980s, and then launched in 1990. What does that do? Yeah, okay, anyway. With the current spare parts and the last servicing mission in 2009, we think it will last for another number of years, maybe through the end of this decade. So it's been a human lifetime size project, right, for a good fraction of human career. The Webb telescope was first conceived in 1996 and then funded by Congress. It been a good 22 years to get it to the launch pad from the first conception and funding. And it has propellant on board. Well, it was designed for 5 years with a goal of a 10-year lifetime. It has propellant on board, it turns out, for 27 years. So I don't know whether I will not have retired before that time. But if all goes well, it will work for a little while. So and of course, it was named after the fellow here next to JFK, who the second NASA administrator, James Webb, who stood up to JFK when Kennedy said, you know, he actually used a 4-letter word that I can't repeat here, but it's on the White House tapes. He said, I don't give this word to go to the moon. I just want to beat the Russians. And then Mr. Webb said, no, Mr. President, if we go to the moon, we must find out what's there. So he invented space science, James Webb, and that's why the telescope is named after him. So the telescope is about 2.5 times bigger in diameter than the Hubble mirror. And therefore, as you heard in the earlier presentation, the shorter the wavelength, the better the resolution. And at the same resolution, at the same wavelength as Hubble, it will be 2.5 times as good. And at longer wavelengths in the near mid-infrared, especially in the near infrared, it will be significantly better than Hubble in resolution. So it is an infrared telescope, and it doesn't look like Hubble at all. It's made out of these 18 segments. So here's where, for the sake of time, I'll skip through my chart, but I will do so without further comment for about 15, 20 charts. If somebody has a question, please yell, or Tom or Woody, you'll tell me. I believe you had a talk on this by my coworker, Rolf Jensen, last year. At that point, we didn't have a whole lot of images. We have a lot more now. By the way, this particular one I want to talk about for a minute because I take credit for it. In my summers, the last 22 years, I've worked for the Nobel laureate John Mather, who was in charge of this program. And we had a hunch that the project would be, this was in the early 2000s, that it would be delayed. We didn't know it was going to be delayed by 14 years. But I figured it would be staring at the ceiling for longer than it needed to. And indeed, it was in Goddard Space Flight Center for many, many years, waiting for all the other parts to come around. So I had asked for mirror covers, so we could cover the mirrors against dust. And Mather didn't want to do that, but I won the battle. So we have mirror covers on the ground on top of the beryllium mirrors. And here you see 2 NASA employees in bunny suit very carefully mounting or dismounting a mirror cover. They do that like Olympic divers on diving boards. This is also a good one. You might not have seen it. This is the Webb on the merry-go-round in Building 29. Goddard Space Flight Center. Also, you can see the NASA logo or meatball on the wall there behind you with the guys in bunny suit right in front. And this is the team with John Mather on the right cracking the whip. And now you can see the mirror is pointing at the wall that we just looked at, and you can see the NASA logo is there and it is magnified. So the telescope works. Yeah, this was our first test. Thank you very much. I was even more glad that we had the mirror covers, because during the snowstorm of January 2016, this is the largest building NASA has on the Goddard campus. It once upon a time housed the entire Hubble Space Telescope for testing in the early mid-'80s. And there was, during the snowstorm, 2 Olympic swimming pools worth of snow on the roof. Fortunately, there were no leaks and we had the mirror cover. So anyway, the telescope was well built and well protected and significantly delayed for various programmatic reasons that I won't get into. So if you do have questions about the hardware that you didn't get answered before, please raise your hand or speak up, okay? And Tom will let me know if there's anybody on the internet. One of the good things we will do, as you will see, is take images and spectra at the same time. And the images, of course, are just that, as you heard in the earlier presentation. The spectra work as following. If you know there is a galaxy or a star, you know, the thing with the diffraction spikes are the stars, and they're sort of like the drops on the windshield of your car when you drive to intergalactic space. Everything else in that image is a galaxy. And if you know where the galaxies or the stars you're interested are appear, then you can use these little micro shutters. They're a quarter by half a millimeter across, and they can open and close magnetically, mechanically, and then let the light through. And the light then goes through a prism, and each one of these little holes with the galaxy inside turns into a cigar spectrum that goes as a function of wavelength from left to right. And so you can analyze the light as a function of wavelength for studies of their chemistry or even the distance via their redshift. So for the sake of time, I will go through some of the, this is, by the way, how we transport that thing. It doesn't fit in an overhead compartment. The whole thing goes on a 36-wheeler that takes 2 freeway lanes into a C5 and goes from continent to continent and testing chamber to testing chamber. The last test we did was here in Redondo Beach in August of 2020, where it was put on a shaking table to make sure horizontal and vertical vibrations were properly tested for. And this was actually one of the most dangerous aspects of the program, other than the launch itself, because if there had been an earthquake right during this moment where the telescope was driving on a grocery cart across the Northrop parking lot, that would have been bad. Well, it wasn't a grocery cart, but anyway. So everything went well. We mounted it on the shaking table, and then lo and behold, there was an earthquake after it got mounted, the El Monte earthquake of 2020, but it was only a Richter 4. We could measure it, of course, but no damage was done. Anyway, next thing you know, the telescope was built, was moved by ship from San Pedro, the Long Beach Harbor, through the Panama Canal to Kourou, which is north of Brazil, French Guiana, and it was launched there on Christmas Day 2021, a marvelous present at 5 in the morning for us. So there it goes. It was a perfect launch. The French really did a good job in making that 100% accurate. So as a consequence, instead of having fuel on board for 10 years, we now have fuel on board for 25 or 27 years. Anyway, so this is sort of a last farewell picture of the telescope above Saudi Arabia and the, unfortunately, currently very restless Gulf of Aden and Africa. But there it is, and that was taken by a camera in the upper stage of the Ariane 5. So the first thing the Webb did after a couple of months, well, it had to deploy its sun shield, of course, and the mirror had to come fully into focus. And then they started this long and laborious process of focusing it, where each of the 18 mirror segments, which are 4 feet across, 1.35 meters, would produce an out of focus image of a star. And then the exercise was with very nanometer precision type motions of the redundant mechanisms to get each of these stars in focus. And that took a couple of months. But here it is to the left, you see the 18 mirrors in focus individually. And then when you change their angles, you co-align them, you get over there to the right, a perfectly focused star. This was in March of 2022, 2 years ago. And then some of my buddies here on March 16, so almost 2 years ago, they took a more detailed image of that focused star, and they were, kind of interested in that. They were planetary astronomers. They cared about exoplanets going around stars, but they were actually more excited about all the galaxies in the background here. And we'll get to that. There's lots of galaxies in the background in any of these images. In fact, in any of these images, you'll find a lot more galaxies than stars. The only exception here is this test image that shows everything at once with the Webb telescope, what it has on board. In a field, in a companion galaxy to our own, the Large Magellanic Cloud, which is at a distance of 160,000 light years or so. And this is the European near-infrared spectrograph, which also NIRSPEC, acts like an imager. The NIRCam made by Marcia Rickett, U of A, the mid-infrared imager also made by Europe and JPL in Pasadena, the Canadian near-infrared sensors, which also back up as a guide probe to hold the telescope still so it doesn't move during the exposures, which is done here by the fine guiding sensor. And this NIRIS is part of the Canadian package that also functions as a redundant spectrograph that we use. And I think Rolf Jensen talked to you about that last year, so I'm not going to talk about it right now. This is just an example to show how much better the Webb images had gotten compared to the Spitzer image to the left. That was an 85 centimeter telescope. This 6.5 meter telescope, and you can see the significant increase in resolution. All the stars bright over here are much sharper here, and many more faint stars show up. And indeed, a lot of gas and dust between the stars. So this is now not in our own galaxy, but in a neighboring galaxy. And here you see about 100 of these little micro shutters open on stars in the Large Magellanic Cloud. Actually, this is the galactic center, I'm sorry. And again, you can study the spectra and the motions of these stars and the chemical composition from left to right. So every image here gets turned into a cigar. Very efficient. So unless there is questions about sort of this bird's eye quick overview of the hardware, which some of you had before, we will now get to part 2, the cosmic circle of life. So are there any questions at this moment on the first part? I know I had to race through that a little bit for the sake of time. I'll slow down a little bit from here on out. Anybody? How about on the internet? Everybody good? All right. So before getting to the cosmic circle of life, can we make that box go away? Yeah, I've probably done that too much. Oh, here we go. Oops, let's get this straight. This periodic table you learned about in high school is not actually the real one, right? Hydrogen and helium, which are called in blue here, the 1 or 2 proton atomic elements, are the only ones that were made in the Big Bang. And everything else with the different colors was made predominantly in dying stars. In green, you see the chemical elements that were created in low mass stars like the sun. When they eject their outer shells, the sun will do that in 4.5 or 5 billion years. So no need to panic yet, no need to sell your real estate just as yet, but it will happen. And in yellow, you see the chemical elements that are predominantly made in supernova explosions, also in white dwarfs. So that stuff here in gray comes either from supernova remnants exploding massive stars, or white dwarfs, which are stars like the sun after they throw out their outer layers, and sometimes they merge or borrow material from a companion star. Many stars are actually double stars, and that then leads to another type of supernovae. And then there are neutron star mergers in purple. So that's how the periodic system came to be over cosmic time. But I told you, this is not the real one. This is the real periodic system. Yeah, hydrogen 76%, helium 24%. That's the outcome of the Big Bang. The Big Bang didn't last long enough to make anything heavier, or short enough to make anything less than 24% helium. Everything else, the bottom of the periodic system, I'm mentioning a few that are rather abundant: carbon, nitrogen, oxygen, magnesium, iron. I had most of that for breakfast this morning. I assume you did too. And so we humans are made literally out of cosmic stardust, stuff that didn't get made in the Big Bang, but made in stellar explosions of various kinds or neutron star mergers. Yeah, so there you got it. That's the real periodic system. Keep that in mind. It is that 1% of the elements, so hydrogen got reduced from 76% originally to 75% today. The rest made it into stars and in these heavier elements, which mostly, when the stars are burning their nuclear fusion, makes it outside the stars in explosions or shells, as we will see, that will form a new generation of star, and therefore you get the cosmic circle of life. So to the left, you most certainly seen this, and probably also had Paul Scowen or Jeff Hester here as a speaker. They made this image with the good old original Hubble Wide Field Camera 2 in 1995. And that probably is the most famous Hubble image ever made here at ASU, not by me, but by Hester and Scowen. And it's one of the only ones, I think, that ever made it onto a US postage stamp. To the right, you see the same image, but now not in the UV optical, but in the near infrared. And it looks kind of the same. But what you're looking at here is light-year-long pillars of cosmic dust that are being shone upon by bright stars on the top, not necessarily all shown here, that due to their radiation pressure, sculpt and press down and sculpt these long-shaped clouds of gas. And I'll use my cursor so the internet can see it too. At the end of these little fingers here and there and there, in the infrared, you can see that actually new stars like the sun are born, yeah? So these massive stars, which kind of look blue in the background here, do the shaping, and new stars like the sun are born because of it. We call these massive stars, I call them at least, the cosmic fraternity members, because they live fast and they die young. Please don't do this at home. But these bright stars, these massive stars that were born before the sun, are the ones that actually shape these clouds into a form where stars like the sun, as you can see at the end of that finger, are forming, and they're just newly formed. So that is part of the cosmic circle of life. Here you see it in the mid-infrared, 8 to 15 microns in wavelength. That's maybe 20 to 30 times longer rather than red wavelengths than what the eye can see, but you can see now more clearly through the dust, as you could also see here. The optical shows very thick dust pillars. In the infrared, you already start peering through that dust. As you know, a sunset is red because the red sunlight is going through the atmospheric dust on Earth more easily than the blue light, and you see that here even better. Except now in the mid-infrared, the clouds are not only transparent, but the stars themselves don't shine as much in the mid-infrared, but the dust instead glows a lot, and it glows because of its own heat or warmth. It is typically between 40 and 50 Kelvin. Here's an example of those cosmic fraternity members. This is a couple of thousands of massive stars, much more massive than the sun. And this is now also, again, in the Magellanic Cloud, 163,000 light years away. And at the edges of that cavity, it looks sort of like a dark blue Christmas tree. It was our Christmas card a couple of years ago. You can see that there is other pillars now in not our own galaxy, but a nearby galaxy where also sun-like stars are being formed. And it is all the courtesy of these more massive stars that live fast and die young. Yeah, here you see this process in full glory. The bright stars are on top and even off the chart. The cosmic dust and gas is here in brown. And then some of the new stars that are forming are these little white dots in that brown beachhead. I call this the cosmic cliffs of star formation is what NASA calls it. I call it the cosmic beachhead or cosmic circle of life. If you look at this part in the mid-infrared, where you look through the dust more clearly, indeed, lo and behold, you see that many stars, the mass like the sun, are forming out of this gas and dust. And many of those don't come singly. The solar system is somewhat unique in the sense that we don't have a second star in the center. We're just, thanks God, only a single star. It would make the orbits a bit chaotic. Most stars come as double stars, or they form in star clusters. The sun was not so unlucky. All right, here's another example of a constellation you know, Orion's trapezium, 1,300 light years away. New stars are forming on the edge of this dusty cliff, and if you magnify them highly enough, and you take a spectrum, this is done in the mid-infrared, you can actually see that some long carbon chains like methylcation, I'm not sure I pronounce it correctly, is actually found there. Some good number of exotic molecules are found in these rather dark and cool cosmic cradles. This is the Hourglass Nebula, 460 light years away with some phone number name. This is a protostar, 30% of the mass of the sun, just about forming right now, just about starting to glow on the inside due to nuclear fusion. It's only 100,000 years old. So this is roughly what our solar system looked like 4.5 billion years ago when the sun just started. And the planetary system, as we will see, was not made out of this gas. This is just gas that's illuminated like an hourglass by the, a nascent star inside, but a little disk is forming here along the horizontal plane that I'm indicating with the cursor. And that is where this star L1527 will be developing its own planetary system, which is not quite there yet. So here we have also star formation. Here's a much more spectacular version of that. This is in Rho Ophiuchi, the Ophiuchus dark cloud, only 450 light years away. And along this darkest, very brown filament here is where new stars are forming. There's a couple have already emerged. There are other ones coming out. And you can see here the process of the circle of life, cosmic circle of life in action. Inside this nebula, fairly complex molecules have been found. Polycyclic aromatic hydrocarbons, PAHs as we call them, just long carbon chains, not alcohol or ethanol, but something like it. By the way, the interstellar medium contains more alcohol than is required to keep our fraternities drunk for 100 million centuries or so, right? I mean, there is alcohol in the interstellar medium, but lots of other carbon chains, right? And so, anyway, here's another example of that. This is Herbig-Haro, a newly forming star. In this case, the central star is already glowing. In the center, it's not an accretion disk, it's the planetary debris disk is already spinning, and material is being squirted out at these, plus or minus 45-degree angles from the vertical. And that's what happens when a young star starts. This is well before its planetary system is formed. We can clearly see that a lot of surrounding ambient gas and dust is involved in that process. Not all of that gas and dust mix it into the central planetary system. Some of it just gets spit out. It's a fairly common phenomena that's just a consequence of the law of conservation of angular momentum. Anyway, here's a star you can see with the unaided eye. I'm sure you've seen it all on a good winter night with telescope. It's a star Fomalhaut. I forgot the name of the constellation. My geography in the sky is all rusty, but somebody can tell me where it is. But down there in the south, somewhere in the fall or in the late spring, late autumn, and you can see that this one is surrounded by infrared glowing and mid-infrared glowing debris disk that doesn't quite show planets yet, but it shows rings where planets are scooping themselves up from the dust and gas that's there. And lo and behold, you can indeed begin to see a little orange and blue knot here at the two different wavelengths where a protoplanet is forming. So if you wait long enough, this star will have real planets, but not just yet today. This would be where the giant planets form. This is what a situation like this looks from the side. You can see the horizontal disk is where the dust and the gas is that's agglomerating into planets. And in this case, the telescope keeps what we call a cold finger, basically a small dime-shaped blocking device that blocks the light of the star, so you can see everything. The star is not actually visible now because starlight was suppressed. You can see the surrounding disk that is making the protoplanetary system for this star, which is only 32 light years away. So you can see it quite well. This is on scales of 5 to 60 AU. Our solar system, if you include Pluto as a planet, which it isn't anymore, is about 40 AUs in radius. Here's an image of Mars. This was done with a NASA mission, the MOLA mission, I think. And here you have an image in the near infrared at short and long wavelengths. So the good thing about this is with Webb that you can actually measure the temperature and the weather on Mars, because this changes over the seasons. Of course, Mars goes around the sun almost every 2 years. And indeed, it's, summer and winter, fall and spring last about 6 months each. So the infrared telescope is like night vision goggles, a very good thermometer. Another thing it can do very well is to measure at these wavelengths, the colors of the infrared light, the impressions of water and carbon dioxide. As you know, Mars, like Venus, although Venus is much denser, have a 96% carbon dioxide atmosphere, so not a very friendly place to go to. Elon Musk is going anyway. I hope he brings some oxygen. But there may be a teeny bit of water, although it doesn't look like an impressive amount. Of course, Mars is cold enough that most of the water will be tied up in ice. So we need to do a bit better job looking for ices there, which the telescope can also do. Here's Jupiter. This was the Webb image that came out in August 22. You see the North and South Pole, they show these magnetosphere, very strong magnetic fields. Jupiter is 12 times the size of the Earth, weighs about 330 times as much, I think. And it spins in 10 hours instead of 24 hours. So the inner part, because it's kind of metallic hydrogen, creates this enormously strong magnetic field. That's the great red spot that you saw also in the earlier image that the speaker showed. And that is a storm that Galileo discovered in the 1600s. If you want to have a job with solid job security, become a weatherman on Jupiter, because then you can say that the weather tomorrow, like yesterday and like 400 years ago, will be the same. That is not true for our hurricanes today. That's Saturn. I'll go through this a little more quickly. Has a lot of rings, of course, and a number of larger moons visible. The inner rings over there are actually moons that never managed to form during the tidal forces of Saturn. Rings are actually quite common for giant planets. Here's Uranus, also has its own rings. So having rings is more of a rule rather than an exception, except Saturn has the most predominant ones. The ones around Jupiter and Uranus and Neptune are not nearly as spectacular. You can see the North Pole on Saturn here is actually the hottest point of the planet because its axis is tilted by more than 90 degrees. So that part points at the sun for half of its 84-year orbit. This is the planet Neptune with its brightest moon Titan, which is actually brighter than the planet itself in the infrared because of all the methane that it has on its surface. And on the moon Triton, it actually rains methane, we think. And so it does on Titan as well, the moon around Saturn. There's an enlargement of Neptune. You can see it also has rings and some funny looking methane clouds in the upper atmosphere here. So we get a few more slides on the exoplanets and star formation, and then we go to the Eyes of Einstein. With the suppression of the starlight at a known position with that little coin-like thing, the coronagraph, we can actually see the surrounding planets directly. Here's an example for this particular phone number. And here's a spectrum of another star like that in the infrared. And again, you can see there is, in this case, a good bit of water. In fact, the spectrum is predominantly water features. But I need to caveat that a bit. The temperature is 1,000 degrees Fahrenheit. So this water is really steam. Yeah, it would not be a good place to live. And it's half the Jupiter mass. So it's not a planet with a significant solid surface either. But it's interesting. So now let's get to the end of the circle of life. At the end of the sun's lifetime, it will have burned up all the hydrogen in the center. Hydrogen in the outer shell turns it into helium. Then it burns helium into carbon, nitrogen, oxygen, etc. As I said, based on the periodic system. And the carbon, nitrogen, oxygen will in the outer shells also cause the shells to expand when helium burns into that. And at that stage, we get the diameter of the star to become 100 times larger than the current diameter. So the star, this is star like the sun, will swallow the Earth and maybe also Jupiter. We call this the asymptotic giant branch stage. This will happen to the sun in 4.5 or 5 billion years. Yeah, just so you know. To the left is the infrared, the near infrared. To the right is the mid infrared, up to 28 microns. You can see this happens in phases. Shell after shell after shell gets expelled. It's a rather unstable process. Needless to say that this is the end of the solar system. So therefore the cosmic circle of life. But this newly expelled dust of the heavier elements, which is very visible in the near infrared, will lead to the formation of future stars and future planets. So I will put this succinctly in this verse from Genesis here, which I couldn't resist to show. For dust thou art, and unto dust shalt thou return. This is not only true for stars and for planets, but it's also true for people. Yeah. So just for the cosmic circle of life, that really is happening for everything in the universe. Here you see one more view. The star that's actually doing it is not the bright one, but the fainter one. But the bright one will do it someday in its lifetime as well. The ring nebula we saw in the earlier talk, ground-based exposure. Here's the Webb exposure. Also an old star just like the sun. That's the culprit that is shedding out its outer layers. And it is done with burning its helium. And what's left over will be a white dwarf and this spectacular amount of dust in its dust shell. Here's a different kind of star. This is a star 30 times the mass of the sun. It hasn't turned supernova yet, but it will do so in the next few 100,000 years. We call it a Wolf-Rayet star. It's very massive, very blue. It's also probably rotating very fast, and it's already expelling its outer shells. When this star goes boom as a supernova, because in the end, you know, a star like the sun will burn hydrogen for almost 10 billion years, and then helium for a couple of 100,000 years, and then carbon, nitrogen, oxygen shell for a couple of years, and then heavier elements all down to iron in months to weeks to days, and then suddenly the process stops. Iron is the heaviest element you can form in the periodic system due to nuclear fusion. Anything beyond that takes other kinds of energy that actually costs more energy than it delivers. So when the inner core of the star has become pure iron, it has nothing else to do but shed out the outer layers and let the inner part implode into a massive black hole. This happened to this supernova 1987A, seen in the Magellanic Cloud in, you could see it from Chile. I've seen it. It is quite spectacular. It didn't look like this in 1987. It was just a bright dot. But since then, the outer layer have expanded like this to this beautiful ring and hourglass shaped, again, part of the cosmic circle of life. This is sort of the last picture on that topic. This is the Cassiopeia A nebula, seen primarily in the infrared. It's also quite spectacular in the optical. So this is a rendering of all these dusty elements, you know, carbon and upwards in the periodic system that's being expelled by a star only a few thousand years ago, I think. So we can now look at this, how this happens in other galaxies. Galaxies are typically 100,000 light years across. As you know, if this is not a galaxy just like our own, ours would be a little denser spiral, but our sun would be in one of these spiral arms formed out of the red gas and dust you see here. And here in the mid-infrared, the bottom panel, you see the same galaxy, except now you see all the heavy elements that have turned into dust particles, which are highly radiative in the mid-infrared. Spectacular images. And this last month, this image came out of a whole slew of galaxies where this one would be most like our own. Again, the sun is sort of halfway between the center and the edge, one of these many dots, 100,000 light years in diameter for the entire galaxy. This is not our own, but ours would just like that. And here's a whole bunch of them, image like that. They don't quite all look the same, but they all have sort of this bluer center where stars have already formed and are aging, and then the outskirts where the dust is being expelled by the sun-like stars and the very heavy stars. All right, I'll pause for a moment to see if there's any questions, and then I'll spend a little shorter time, but very important time, on what Webb has done with the Eyes of Einstein. So, Woody.
Questions at this stage?
I go too fast for you guys. Yeah.
Can you explain cosmic ray fission on the periodic chart? You said it showed cosmic ray fission for elements like boron.
Sorry, I need to turn my cell phone off because I hear you also.
Oh, sure. Yes, cosmic ray fission was one of the reasons that boron was produced.
Yeah, so that was implicit in the chart of the periodic system. Cosmic rays are byproducts of supernovae. Oh, yeah, what happened? Okay, just like this. So cosmic rays are byproducts of, well, first of all, the sun makes them because the outer layers past the photosphere, the surface, if you wish, that we see, it's not the surface, the atmosphere of the sun. The outer parts are hotter, they get up to 1 million degrees, and they expel because of the strong magnetic field of the sun. They expel particles, mostly protons and helium particles, alpha particles, which we detect on Earth as cosmic rays. But supernovae are also very good at that. They expel, including very high energy cosmic rays. Most of those, I think, they come from gamma ray bursters, where there's various kinds. There's merging neutron stars and other catastrophic events where very massive stars that are rapidly rotating go supernovae, and they don't just produce a shell, but they actually produce a relativistic jet of material that we call a gamma ray burst. And these are, in fact, momentarily the brightest gamma ray sources in the sky. And they also produce cosmic rays that make it to Earth. So the cosmic rays we get here on Earth are a mixture of what comes from the sun and from these other exploding phenomena. Yeah, and boron and other, so boron is actually, I probably shouldn't go back for the sake of time, but you've seen that periodic system that wasn't like the high school one, but with the relative proportions. Boron is very rare, and it is not made in the Big Bang. Lithium to a very small fraction, and beryllium is, but boron is not. So it really comes from, no, I need to go back to the chart because I don't recall. Maybe you know better than I do, but I'll erase to it. Here we go. That one. Boron is orange, and that's cosmic ray fission. Yeah, so where cosmic rays get split by other particles, it's a byproduct. And I don't recall which reaction does that. But if a heavier particle gets hit by an alpha particle, it can produce a boron core that has 5 protons and 5 or 6 neutrons. Yeah, good question. Any other questions? If not, we'll go to the Eyes of Einstein, which is the second part of the talk that deals with the faraway universe. And Einstein predicted a whole bunch of things, many of which he doubted. One of which was the expansion of the universe. He predicted it from his theory of relativity in 1915, and then Hubble discovered it in 1929. Einstein initially didn't believe the prediction, so he put in a constant that said, well, if I set this constant to the right value in my field equations, I will not get the expansion. Then he later declares that his biggest mistake, it wasn't actually a mistake because the constant is non-zero. We currently know it as the cosmological constant or the dark energy. Einstein was really struggling with this one. And the other predictions he made was black holes. Actually, other people did that with his theory, and he really distasted the concept of a black hole. Now we know today that there are common features. Every massive galaxy in the center contains one. And then, of course, massive stars will dump smaller black holes as leftovers after they go boom. And then he also predicted, this is something he really didn't want to predict, but one of his colleagues asked him, what happens if you have a massive object that bends the light, as your theory predicts? Will you see the light behind the object split in various paths and see various different images like in the cosmic house of mirrors? He predicted that, but he starts his paper by saying, well, I don't think this can ever be observed. So it's a fairly, innocuous prediction, but I'll do it anyway. So in all of these things, Einstein was exactly right, even though he didn't initially believe his own predictions. Anyway, so here's a collection of galaxies. These are now 40 million light years away from us. 4 of them are at the same distance of a couple of 100 million light years. 1, 2, 3, 4. This one is a bit in the foreground. This is a near-infrared image. We call this the Stephan's Quintet. It's a cosmic train wreck. Very soon, well, in the next few 100 million years, these things will merge and form one giant galaxy. What's going to happen during that process? Oh, well, you can see that here. And this is more in the mid-infrared where the dust is more prevalently visible. This top galaxy here is actually developing a very bright star-like object. Indeed, this is the diffraction spikes that we talked about earlier, that you also have in optical telescopes. With the Webb telescope, because of the hexagonal structure, you get 6 diffraction spikes. And that diffraction spike is actually not a star. It's part of the accretion disk around the supermassive black hole in the center of that galaxy. And again, that is rather common. Here's a beautiful spiral galaxy, not our own, but one kind of like our own, with a little bar in the center, beautiful open spiral arms. This one is 48 million light years away. Of course, if we were in this galaxy, which we're not, we would be sitting here somewhere. Again, you're looking mostly at the dust produced by the star, so that 1% of the heavy elements. Here's another one with a bigger star-like object in the center. This now contains a fairly massive, supermassive black hole. I will refer to them as monsters sometimes because they eat prodigiously. Here's an especially obnoxious one. This is some telephone number, NGC, spiral galaxy 220 million light years away, but it got this fantastic bright disk in the center. This is a supermassive black hole of the order of 10 million solar masses worth of matter that made it into the Schwarzschild radius, which of course is the radius where the matter is so dense that not even light can escape. The escape velocity would become larger than the speed of light, and therefore that region is always black. We call it a black hole. Nonetheless, stuff that falls in and hasn't fallen in past the Schwarzschild radius yet falls in at very speeds, very high temperatures, and produces this nearly infinite amount of energy that you can literally see to the edge of the universe. Let this sink in. If this were our own galaxy and we were sitting at the edge of that black hole and it had an active accretion disk like that, the accretion disk would not be bigger than about our solar system, 40 astronomical units. Now, last time we went to Pluto with spacecraft, we went 40 AU away from the Earth, the sun, made the spacecraft look back. There was the sun, a dim star in the sky. If you're at the edge of this accretion disk, 40 AU away from the center of the black hole, you see that enormous, hot, amplified accretion disk shining with the brightness of 1 trillion solar luminosities. Yeah, that's a good place to get a suntan. Yeah, go ahead. Right where is the brightest spot? It's very counterintuitive. Black holes are less than 0.1% of that 1% of the mass of the universe in the heavy metals we talked about. Yet they are capable, and of course, by definition, they're black because light cannot escape. But the material that falls into the black hole, I have a cartoon a little later on, but I don't want to jump to it now for the sake of time. Once material falls into the black hole, just before it falls in, it heats up to temperatures of 100 million or 1 billion degrees, and that makes it almost infinitely bright. So wherever the bright spot is inside there, invisible, is the black hole. Yeah? I hope that's a good answer. Don't do this experiment at home because, you know, the sun will give you skin cancer in 70 years, or if you're not careful, this will give you skin cancer in a picosecond. Yeah, be very careful with this one. Anyway, so this is an image made by our team, including one of the folks in the audience, Jessica Berkheimer and Bill Keel. 2 galaxies, a spiral just like our own, not our own, but just like it, 220 megaparsec, but 700 million light years away. An elliptical galaxy behind it that we use as a flashlight to image and find the attenuation of the amount of dust from all these stars that we talked about in this foreground spiral. So we use it to map the attenuation of the dust. And we found in the Keel paper that the dust particles in these galaxies are a little smaller than in our own. Jessica has counted the number of globular clusters in this background elliptical, and she found more than 150. And we're doing this same exercise now also in other fields. Globular clusters are in fact the oldest inhabitants of a galaxy. They were the first little star clumps of 100,000 million, maybe 5 million stars that formed within the first billion years after the Big Bang. We saw something else. There was this arc-like feature with a counter image here, right around the most massive center of that elliptical galaxy, and that is a gravitational lens, precisely what Einstein predicted. There is, more than 100 billion stars worth of mass here, and they bend the light of a galaxy just like this or that happens to be behind the elliptical, and therefore the light comes to you via 2 different curved paths, can even be more than 2 different curved paths. And that is actually quite common, we found. This image, Tom and Woody, you tell me when I need to stop, right? You got to hear this story. So this image was made by one of my guys in my team. He planed it, and the other guy took the data and reduced it. This was done in June of 2020. This was 12 days, June 30th. There's 12 days before the data was supposed to come out. It was supposed to be released on July 12th, 2022. It's a cluster of galaxies, 4.5 billion years away, with many objects in the background gravitationally lensed into arc-like features, spaghettified light, if you wish, of light that doesn't come straight to your eyes or telescope via a straight path, but via these curved paths that makes the galaxy looks like arcs. So this image was so spectacular that our guys sent it up to the director of the Space Telescope Science Institute in Baltimore, who fell off his chair and sent it up to Goddard Space Flight Center, and they fell off that chair. They sent it up to NASA headquarters, who couldn't believe it, who sent it up to the OMB, who was very flabbergasted, and they sent it straight to the White House, and the White House sent it to the Oval Office. And the next thing Joe Biden himself, president, revealed his image a day early. So there we go. Call it the Biden cluster. Yeah. Fortunately, he was called to the Situation Room a few minutes later because there was something else going on. So he didn't scoop us on our Nature paper. He left it at that. But yeah, this got everybody's attention. It wasn't my image. It was done for the public good, but some of our people were working on it. And that, by the way, is Hubble. 100 hours, Webb, 20 hours. Yeah, you can see the enormous increase in contrast and brightness and resolution. I have another example of that, even better than this. So that was the first Webb image, the Biden image. Here's another cluster. Oh, and I forgot to say, in the context of the cosmic circle of life, this cluster, Max with some phone numbers, Max, won't tell you what that means, but there it is. The light of these galaxies, when it was emitted, distance of 4.5 billion years, was already 9 billion years old, right? So the Earth today is 4.5 billion, 4.56 billion years old. Those galaxies were back then already 2 times older. Today they would be about 3 times older than our own sun and our own solar system, yeah? So if you want to put it differently, we, the solar system, are kind of a cosmic afterthought. We're the late young kid on the block. There's much older, much bigger galaxies out there. Here's another example, 5 billion light years away for that cluster, and it images a pair of galaxies seen under 3 different angles. One pair is seen here, one pair is seen there, and another pair is seen in box number 3. These are 3 of the same pair where the light path comes through 3 different angles at your telescope. Yeah, there is a brighter yellow one and a fainter redder one. These ones are redshift 10 when the universe was 11 times smaller than today, the first 400 million years. Here's another one, this is even better than that. Einstein also predicted that if in the gravitational landscape, not only can the gravity of these galaxies distort another background galaxy into one of these beautiful spaghettified arcs, but there is in the relativistic landscape a certain line or a mathematical surface, we call it the caustic. If a star is right there, its magnification is so great, its light can arrive at your eyes via so many independent paths that it can essentially be magnified by a factor of 5,000 or 10,000. That happened to that star Arundel, which is the early, old ancient English word for morning star. And that was seen at a redshift 6.2 in the first billion years. That is the image of a single star. Now, mind you that this star was a factor of 5,000 below the detection limit, but because the magnification was more than 10,000, we could see it. Yeah, and it will only be visible for a certain period of time because before it moves out of that infinity surface. Here's an even more exotic example. Again, an ordinary cluster of galaxies, pretty compact with 2 clumps, about 4 or 5 billion years in the past, nothing to write home about, not that close. But there is a highly magnified infrared source, 2 of them actually, these sausages. And I really need to use my laser pointer, or I'll rather use my, what is called mouse. There's a little dot here and a dot there right above my hand, or a dot there, I'll show it on the screen. That is a supernova, redshift 1.8, seen 3 different times. Again, 3 different light paths. And then once we found this in March last year, we immediately asked the director for a couple of other exposures. We got those in April and May. So now we have a light curve for this type 1a supernova, the white dwarf type, with 9 measurements. We actually have submitted a paper to Nature with a measurement of the Hubble constant 10 billion years ago. I can't tell you what it is yet, except to say that my friend Adam Rees, the Nobel laureate, who was originally on my team and then left the team because he had some babies, and he said, Roger, I'm too busy. He came back the other day, he said, well, I'm going to be part of your team again because I like this result. He's the one that you may have heard about the Hubble tension. If you ever had a talk on the Hubble tension, the Hubble constant today is not the same value. It's off by 10%, which is highly significant from what we measure to be in the early universe, in the the microwave background, the kind of stuff that Tom studied for his dissertation. That 10% is very significant. We don't know why that is. There's still something wrong, not with relativity, but the way we use the equations and plug in the parameters. Hopefully this supernova and another one that we just discovered will give literally shed more light on that. There's another one that we've just found in a cluster that Hubble first observed in 2016. Look, supernova, no, same supernova goes off 3 times because of the 3 different light paths. And here, 7 years later, we find another one, different supernova, now a redshift 1.9. The cosmic age there is 3.5 billion years. And again, we hope here to make a good measurement of that Hubble expansion factor at this enormous distance. And there's still a couple of things shaky with our cosmology. We don't quite know what to make of this. Is probably one of our best images. Came out in August last year. There's a press release, you can read about it. Very massive cluster, almost halfway back in Hubble time. An ordinary dusty spiral galaxy like our own, but forming stars a little bit more than average, happens to be behind this clump over there and turns into this horseshoe. We call it El Anzuelo, or the Spanish word for fishhook. The cluster is called El Gordo, which is Spanish for the fat one. And there's also a highly spaghettified galaxy. Of course, it's highly spaghettified because of the lensing, that we call La Flaca, which is the Spanish word for the thin one. So we got a Laurel and Hardy-like, appearance here. This is actually a great story because when I showed this November a year ago, a year and a half ago, to an audience like this, a guy came to me. His name was Werner Salinger, and he was in his mid-90s. And he said, Roger, I've known Albert Einstein personally. I'm a Holocaust survivor. I came to Princeton with my parents just before World War II started to escape Nazi Germany. And I lived in the same street as Einstein. So on this link here, you can see the story of Werner Salinger and what his impressions of this image were and what he thought Einstein would have thought about this. There's El Anzuelo. For the sake of time, I'll show you our last, probably most significant image. This made it into the New York Times around Christmas time. It actually came out in November. This is the so-called, phone number MAX 0416, redshift 0.4. So it's not that far away, about 4.5 billion years. But you can see the spectacular combination of very red, dusty galaxies and very blue star-forming galaxies, and anything in between. It's just an absolutely gorgeous image. Here's the Webb image, plus the Hubble image together, just to show you the difference between Hubble and Webb. Hubble, of course, renders in blue, while Webb renders in red and green. Here's the 122-hour Hubble image alone, and here's the 22-hour Webb image. So I'll toggle back and forth a few times. You can see how this dusty galaxy and its blue companion become much more pronounced in the Webb image there. I will leave it at that. I'll leave you this thought. Webb is a very sought after telescope. However, there is opportunity for amateur astronomers to submit proposals. It's a bit of a slaughterhouse because 2,000 proposals were submitted and they only approved 10% of that, but some of those go to non-science astronomers that are not actually professionals. So you can ask for a good target and get time. You can see that also Webb in these 3 colors here is much more oversubscribed than Hubble. Hubble had typically 800 or 1,000 proposals per cycle. This is the pile up to the deadline. The deadline is right here. And with Webb, it's 2 or 3 times as bad. So it's probably one of the most successful popular science programs ever done. And I'll leave you with my conclusions and be happy to stay around for questions. I don't think I exceeded the previous speaker in time, but I came close, right? 9:20 here. Yeah, thank you very much.
Questions?
So what's the difference? What's the difference between the pictures where the center of the black hole is very bright and the Event Horizon Telescope, which shows
Ah,
the
yes, thank you for
telescope?
You're asking me the black hole question. So it's all the same gravitational lensing. I think I have a spare chart on that, but if you need to go, I will understand. The spare charts are even more wild than this one, than the ones I've already shown. See if I can find it. You're asking about LIGO or the Event Horizon Telescope, right?
The Event Horizon Telescope has a couple of pictures of black holes that they have published.
Yeah.
They're black in the middle.
Yeah. So in short, I'll summarize this way. These are the cosmic fraternity members I've shown you before, these massive stars that live fast and die young. And they leave, just to put it in perspective, they leave black holes around, the kind of like my kid was a very inefficient eater, only 30 solar masses, and they lived for 13 billion years and didn't grow any fatter than that. There's another kind of black hole. These are the supermassive black holes. Ironically, there's not much in between. And these supermassive black holes are the things you allude to. These are in the center of galaxies. Here, by the way, the brightest dot is where the black hole is. Counterintuitive. I know you can't see the black hole. There's the relativistic jet that squirts out of the accretion disk because it rotates like fool. And where am I going with this? Well, here's the thing you were asking about. With a telescope the size of the Earth, by putting microwave dishes everywhere from the South to North Pole and Hawaii and Chile and what have you, they have for the first time found the smiley face of a black hole shadow. So the dark spot is in fact a black hole, and the little orange arc is the microwave light from the accretion disk surrounding and behind the black hole that gets turned into a smiley face. And so these are supermassive black holes, and this baby was 6.5 billion solar masses. So it's not like a baby, but more like, well, there's a whole bunch of them. They all look star-like, but locally they sit in the centers of galaxies, and they look like this or like that. It's a galaxy like the nearby Centaurus A, which you can almost see unaided eye from the southern hemisphere. Got radio and X-ray jets emanating from the accretion disk surrounding the supermassive black hole. These supermassive black holes are completely different beasts together. They're not like slow-eating babies. They're like fast-eating cats, like my cat. Cats eat catastrophically. They always eat, and they do it secretly. I put this in perspective. A supermassive black hole will eat a Jupiter for breakfast, a Jupiter for lunch, and a Jupiter for dinner. 7 days a week, 365 days a year, 1 billion years in a row. Yeah, that's how you grow to 6 times 10 to the 9 solar masses. And that's what gives you that smiley face gravitationally lensed accretion disk. Yeah, that's a different thing altogether. We can actually not quite make sense of this. It turns out that you may have heard that the Big Bang Theory is broken. That's all bullcrap. It's not. But we do find a larger number than expected galaxies at high redshift. Redshift 15, 20 shouldn't be there. Now, some of these are actually not at the correct distance. You take a spectrum at high resolution, you find out the redshift estimate was wrong, but about 2/3 are at the right distance. I don't think they're galaxies. They're supermassive black holes that are shrouded by their own dust that was provided in very rapid succession by the first generation of stars. So the galaxy isn't actually there yet. To put it in a different perspective, the age-old chicken and egg question, which came first? Most definitely the egg was there before the chicken, or the supermassive black hole was there before the galaxy. Yeah, that's, I think, how the universe started. Don't ask me why, but that's what seems to be happening.
The universe supposed to be only light elements, right?
Yeah, and in the beginning, yeah.
At the beginning.
Let there be hydrogen, helium. That was it. Yeah.
And that was it, right?
And
But
light. Yeah.
and yet you can
Yeah.
make these humongous objects that appear early.
The first generation of stars, which we now think may have been forming around these black holes, maybe originally exclusively there, were very good at pumping out the heavy elements in very rapid succession. But the black holes came first, and we don't know why.
Roger, we've got an online question
Yeah, please.
from Warner Ebner.
Oh, yes.
Is there any credence given in the scientific community to the theory that as the sun becomes a red giant in its later stages, it will push the orbits of the planets outward instead of engulfing them?
Yeah, I don't know much about that. The hydrodynamics of the solar atmosphere, when it expands, the atmosphere is actually quite thin. It will go just past the planet, but heat it up nicely to the point that our atmosphere evaporates. I don't think our Earth necessarily disappears, but it surely becomes unlivable. Yeah, of course, we have more urgent things to worry about. It's already becoming a little unlivable today, but yeah, certainly in 4.5 billion years, it will be hotter than hell, if you want to put it that way. Well, not that hot, but it will be 4,000 degrees or so.
Thank you for a wonderful presentation. I have a question. There was a article in PNAS in the summer about the Webb visualizing 3 dark stars and dark matter.
Yeah.
Could you tell me whether that's been confirmed or refuted with any more images?
Dark stars are still a mystery. We know about a lot of protostars that are hidden behind a copious amount of dark dust, and they haven't even started shining. That Herbig-Haro object I showed you is one of those truly dark stars that are made out of dark matter that has collapsed. I don't think we have seen. We have some evidence. Maybe this is what you're alluding to. And in fact, one of our team members had a paper on this, that there are some direct collapse black holes. So black holes that never underwent this baby process of, burning nuclear energy and go boom and leave a small black hole behind and never grow. We see objects at high redshift, bigger than 12, so the first 300-400 million years, that are so red that the redshift or the dust can't explain it. And the only logical explanation is it's just a pile of matter that directly made it into a black hole and has an accretion disk that is exceedingly red. Those things are rare though, but they are allowed in relativity. Yeah. How they came to be, we don't know. There's a theory that says that there were already black holes shortly after the Big Bang, so-called primordial black holes. And maybe they survived the entire journey of cosmic expansion for a few 100 million years, and then they decided to eat up surrounding matter and became direct collapse black holes, and maybe the centers of these galaxies. Yeah, but most definitely the egg came before the chicken, or the black hole came before the galaxy. Yeah.
More questions?
Roger, you showed one of the slides was an image of a gravitational lens, and then he had, I think it was 3 different supernovae.
Yeah.
That were superimposed. And then how could that lead to a conclusion that the Hubble constant was different in an earlier epoch?
Yeah, this is beautiful relativity in a way that Einstein predicted and didn't want to believe. It's actually, yes, it's 3 images, but it's not. Let me get back to that guy. I'll show it on the whiteboard. Everybody can look for the paper that's in the link here. There's also a press release by Big Think that is even more clear. So this arc has a dot right here. You need to come close to the screen, but it's there. There's more than 5 sigma, and one here and one here. That's 3 different images of the same supernova. Just arrives at your eye. We had 3 different light paths that are not the same length. And not here, but in a paper by Friedel and another slide, the light paths are different by 50 to 100 to 130 days or so. And that then, if you measure the light curve, supernovae have a fairly well-known rise and then slower decline of the total light that they produce in this final explosion. That light curve then tells you what the distance is in terms of megaparsec. And so you know the Hubble constant because you know the redshift. Yeah, it's tricky, but it works. Yeah, relativity works.
Roger, I have a question. Are you using the 21 centimeter line for this aging process, or redshift and H alpha?
We
Or
would very much love to do that, like the kind of work that Tom and Judd Bowman and Danny Jacobs at ASU have done. We think at redshift 17, where they see the signal, which they think is from the global first heating of H1, the neutral hydrogen that formed after the Big Bang, after the universe had expanded and cooled enough, heated by something. My hunch is that it's actually heated by the first black holes. We haven't found candidates for the first black holes yet that are in these neutral hydrogen islands of signal. And that would be one of the things that I think the future radio telescopes are going to do. Maybe Tom can comment on that more, but that was certainly one of the hopes I think we would do. We didn't believe a number of years ago that there would be objects out there, redshift 17. Now we see them everywhere. We just don't know what they are. We think they're hidden black holes or dusty black holes, and they poke enough holes in their own dust because of their relativistic outflows. And that heating heats up the surrounding gas, which I think is the signal they see in the neutral hydrogen. I'm sure Tom has given a talk on this, right? And so, yeah, more to be done there. Yeah.
Any other questions? Let's give Roger another big hand. Thank him for coming.
Thank you, Steve. Thank you very much.
All right, thank you everybody for being here tonight. A couple quick things. Remember, next month we start at 7, so we'll be getting out a little bit earlier as well. The meeting, I believe, is March 15th. And if anybody's interested, there is a group heading down to the northwest corner of Higley and Baseline to the Union Tap and Grill. So if you want to have a little libation, a little bit of conversation, whatever, you can join that group at the Union Tap and Grill. Higley and Baseline, northwest corner. And that's it. Have a great night, everybody. Thanks for being here.